Hello, everyone. So my name is Filipa. I work as a data scientist at Continental, currently sitting in Portugal. So you may know Continental for its tires, the most famous product of Continental, of course. But actually, the business is much broader currently, and especially regarding new digital and smart products. We are building a lot of knowledge there. So I would like to thank DSS for having me here today to share these learnings we have been making in Continental regarding the adoption of machine learning software. So especially in such a big enterprise where normally there are already some guidelines and processes in place for building traditional software. A lot of topics come to the table, new topics when we talk about machine learning software. So I believe that most of you, if you work in this field, you know already that when we are dealing with traditional software, normally someone will ask us with a list of requirements to build basically a computer program where uh, everything is deterministic and you can plan ahead for different potential outcomes of this program. While in a machine learning based product, normally we are dealing with trained models, and this means that their behavior is not deterministic, but instead it's probabilistic. So, of course, if someone asks us to build a self-driving car or any other kind of smart product, a lot of questions come to the table, especially because there's a lot and much more uncertainty when compared to a normal computer program. So if you look at the traditional cycle of developing a software, I would say that if you make sure and you follow these steps that are described here, probably you are able to ensure that everything runs smoothly. So if you plan well, you collect the requirements, you have a good design of your application, for instance, then things will probably run smoothly. For machine learning software, the cycle, of course, looks a bit different. So you firstly need to understand very well the business and to get a look in the data that our client, our stakeholder might have or not. So for me, this is the big difference or the major difference between traditional software and machine learning software. Of course, there are also additional steps, for instance, the data preparation, the modeling, a lot of backward and forward, as you see here. But I think the main difference is that we need to manage a lot of expectations here, to set realistic goals according to the data and according to the business. And because I think this is one of the most challenging stages in building machine learning, I will dedicate my talk to this stage in particular. So to give you some concrete examples and why this is so challenging, at least in Continental, basically, when we come to this point, so when someone reaches us in the company because they want to use some data, they want to be data driven, they want to build a new product that relates to data, we might find a lot of different scenarios. That's why it's so difficult to find a common approach to them. So sometimes we find teams that they have no data at all. They don't have the know-how in this field, and they don't know yet which kind of solution they are looking for, but they know that they need to be more data driven. So in this case, probably we will need to guide them through data collection, for instance. Sometimes we find people where they have the data, they know the potential of this data, but they lack the know-how and they need help in establishing a real solution and to define their product. Sometimes we also meet teams and projects. They already have the data, they know exactly what they want, they simply need the technical support to build this product, to define metrics, and to reach more ambitious goals. So, as you see, this is challenging because we have different contexts, different scenarios, and even when we make sure that this stage is ready, so that we have the data, we have the knowledge and solution and metrics to address. Also, the next steps, I won't focus on more on these ones, but also the next steps from our experience can bring a lot of uncertainty and they can follow very different paths, let's say. So, for instance, when we come to the data preparation, it might happen in some projects that we realize that there are no enough data. For instance, if you want to do some forecasting for a specific market and we don't have enough data for that market, we may need to go back to this part to collect more data. Sometimes the data is there, there's a lot of data, but there are a lot of quality issues as well. And sometimes what happens is that before starting an actual data science project, we realize that before that we need a data engineering project in place, and maybe 1 or 2 years later we can start thinking about applying data science there. And data handling is also a major problem sometimes, especially in manufacturing. It's quite common that we have a lot of data, but they come from old machines, for instance, with older software, and we need also to implement some projects which are not necessarily related to data science. For instance, migrating data to the cloud is a good example that something needs to be done before we go to a data science based project. Also, in the modeling and evaluation, depending on the scenario that we find, depending on the team, and depending on the goal of the project, we might need to do some research. So sometimes there are models ready for deployment that solve our problems. Sometimes we need specific research. Sometimes we find in the mid of our way that we have new requirements, such as speed requirements. So imagine we were thinking about a model that runs in a GPU, and then we need a much smaller model that is able to run much faster and with limited resources. And also sometimes happens that the initial metrics that we defined are not suitable because the circumstances changed. For instance, COVID is a good example of that. And sometimes we need to come up with new metrics according to the business constraints. Regarding deployment, I think this is one of the most discussed topics in machine learning, and it will depend a lot. So the planning can differ a lot. If you want a dashboard, if you just need an endpoint for getting predictions, or for instance, if you need to build a mobile app, it's a completely different story. So basically, this is our challenge. We have a different teams coming to us, different scenarios, different problems, different use cases. And besides showing you the challenge, I also want to share the approach and the solutions we are creating to approach such a big challenge. So one of the things we are doing at Continental is to provide what I call multiple services. So we don't see ourselves as a team of data scientists that are allocated to specific projects, and really what they do is just to dive deep in a technical solution for 1 or 2 years. We see more ourselves as a pool of data experts which are very flexible, available, and ready to do a lot of communication work with anyone in the enterprise that really wants to adopt and use machine learning. So we need to be there to build together with anyone these solutions and to support them in this process. So me as a data scientist, I can do some consulting work where I meet with different teams in Continental, from manufacturing, sales, marketing, whatever, and we help them analyze the potential use cases. We show them our standards, our guidelines, and the responsibility here is completely theirs. We are there just to support when they need. So some of these meetings can evolve, of course, to an exploration phase, where the goal would be to really find what is the biggest problem they have, if this problem can be solved with AI, and if so, start to explore some data, do some preliminary modeling, and see what is the potential for AI there. And next, if it makes sense, of course, the goal would be to build a first prototype. Some teams come to us and they are already ready to jump to this stage, let's say. And yeah, here the goal is to build an MVP so that we fail fast, we check what are the constraints of our solution in the real world, we check the boundary conditions. Here it's shown to provide value to the team or to the company. We shift the responsibility of such project to the data science team. So now, yes, we will dive deeper in the technicalities of the project, and the goal is to develop an end-to-end application. So here things get a bit more similar to traditional software and this development cycle that we know. Once we go to production, so that we have a solution ready to scale, the role of our data science team is mainly to maintain this solution. And what is also very important is to define what we call the final operational state of the product. So with traditional software, normally what you want to reach is a bug-free software that works as expected in all your scenarios. But in machine learning, of course, this can't be the goal. So we need to define what is enough for the model. So what kind of performance is enough to finalize it and to deliver it as the final software that then just needs to be maintained. And this is our common approach, let's say, as a company in data science, to build machine learning software and to help other people in the company to do that and to adopt AI. So this is one part of the story. The other one, which is also very important, is the data science, what we call the standards. So some time ago, I got to know that also Spotify is doing something similar. They call it the golden paths. And I really think that the definition they gave to these golden paths also fits our vision. So basically, the goal is not to force people to use these standards or these guidelines to use these tools. The goal is not to define standards for the sake of it. The goal is that each team that wants to implement AI, they don't need to reinvent the wheel. They can focus on being creative, on being productive, and they can move much faster. So in practice, this means that we provide standards, processes, best practices, guidelines for coding, managing data science products, for tools that you can use according to your field or your solution. And to be more concrete and give an example, for instance, let's say you want to build a solution, a computer vision solution, we have already recommended tools there for you to use. So this means that if you want to label data, we recommend CVAT, but we not only recommend, we have the server in our private cloud ready for you. So you just need to create an account with your company credentials, and you immediately start labeling your data. If you need to develop models, you don't need to run code locally. You don't need to Google Colab. We have something internally which looks like Cloud9, if you know it in AWS. Basically, you just need to create an account again, and you have the development set up, everything ready for you to start writing your own code. If you want to track experiments, there's MLflow server ready. You just need to have a line of code to track and log your experiments. And we are not forcing people again to use these tools, but if they are starting, it's like a no-brain to choose what tools to use. They have these tools that are recommended. They have people that know these tools and how to work with these tools. They just need to create an account and start right away. There are training materials and resources provided by us to use these tools. So the goal is really to move fast. And as a real example that we had, so imagine a business expert that basically it was experimenting some cool stuff in Google Colab. So no knowledge on AI or computer vision. He was trying some traditional computer vision metrics, looking in the internet for tutorials. He used this open source software label image for labeling, and he was running everything locally. So with one meeting and by checking our guidelines, I would say that in 1 or 2 weeks, this person was able actually to set up everything in our private environment with everything installed. They don't need to run anything locally to annotate data in our platform, which is secure, which stores data directly in S3. We recommended PyTorch, where we already have a lot of knowledge, because you wanted to try some deep learning methods, and DVC, TorchServe are other examples of recommended tools. So this is an example where we could really accelerate these decisions of what software to use, how to learn it, and then it could focus on the solution itself, not on the tools. So this is, I would say, a more generic approach that we are using, the standards and also this pool of data experts. And now I would like to give some examples of projects and also share how we are tackling these challenges in real projects in our daily work. So the first use case I bring, of course, is someone that asked us for an automatic tire inspection system. So we have people inspecting manually these tires, but we would like to make this process more automatic. And to give you some context about this, when this team came to us, they already had the images, labels. They had some know-how because they were implementing traditional methods there. They knew that what they wanted was a binary classification. So basically, these traditional methods were trying to find the defects in the tire, and then for each proposal of defects, they wanted to really classify it into defect or not. And the goal was to reduce the detections that were false positives. So even though this team was very mature in terms of knowledge, we took a lot of time, and we are taking a lot of time to dive deep in the data understanding step. So this means to understand which classes are there, which relationships exist in the data. So for instance, we have several tires in the images. Each tire has several images. Each image has several patches, so several detections. And also, we cannot look at the pictures simply as tires. So there are tires for trucks, bikes, cars, so different article types. There are different mold types, which means the mold that produces this article is might be different, and then it might affect differently the defects, of course. There are a lot of different defects and a lot of different severity levels. And why is it so important to dive deep in these details? Because we need to check for these details, to set expectations, to manage expectations, to define realistic goals. So as an example, we looked into the distribution of the defects, and we clearly saw that some examples of defects were not represented in the training test set that was given to us, so in the data set. And here it's really important to communicate this to the stakeholder, to explain that if we cannot accurately detect, so if in a real scenario there is a defect of this type, so let's say type C, and if this defect was not represented in the data set that was given to the model, then it's completely impossible. We cannot expect the model to detect this defect. The same happens with the articles. So if we have, for instance, bike tires that are not represented in the data set, then we cannot expect that in a real scenario, if a bike tire comes with a defect, that we will be able to detect it. So it's really important before we go to the modeling stage, evaluation stage, that we set the expectations using the data. Another learning, and I think something really important, is to focus our work in a sub-problem. So for instance, in this case, the goal was to detect all the defects in all articles possible. So it was very, very ambitious. And normally it's a good decision to try to break the big problem into sub-problems and focus on the most critical problem or the most relevant problem. And we can also guide this focus or decide where to focus based on the data. So use a data-driven approach for this. So for instance, we checked the severity levels here, and we could clearly see that there are two levels which are much more common. So we could ask them, does it make sense to focus on these two? And maybe if we focus on these two, we are already covering most, like maybe 90% of the defects. And maybe it's not such a big deal if we don't detect these ones because they are not so frequent. Or we can also say if severity level 4 impacts the business a lot, if it's really critical, maybe let's focus on this, maybe let's collect some data, because maybe level 1 and level 3, they happen quite often, but they are not so critical to the business. Maybe they are like cosmetic defects where you don't need to completely discard the tire. So apart from that, another challenge that we faced was inconsistent labelings coming from humans. And what we think we should do here is basically to assess the agreement between two human labelers. And if, for instance, they agree 60% of the times, we cannot expect the model to be better than this. Because the model, if he is training on such inconsistent labels, and if even humans, they cannot decide, then we cannot train a model to decide. And here you see 4 examples which are very, very similar, but there's no agreement between the human labelers. So I think the main takeaways is to show to the business what is unfeasible with the current data set, to break the problem into sub-problems. And for this, you can choose like the most relevant or the most critical ones, but you should use data to do this decision. And also use human agreement, if there are human labels, as a guideline to set expectations at this stage. So finally, I would like to bring one last example. So it's still a computer vision problem where we want to take a picture to a tire and detect the DOT number. So basically, this is like an ID for the tire that reflects the dimension of the tire. So to give you some context, I want to bring this example because this is an example where the team didn't have the data when we started to work with them. So the goal is to take a picture to detect some text, like you see here. And what we did was basically to guide them through this data collection process. So it's really important that you ask them a lot of questions, and the data collection will entirely depend on these questions. So if we didn't have such guidelines, they would start to randomly collect data probably. They would learn with this process, but with these guidelines and by implementing the know-how we already have, it's much faster, and you can avoid that every team in Continental does the same mistakes while learning. So what we ask them is, what kind of data are we expecting to get? So for instance, this DOT, is it numbers? Is it letters? Which numbers, which letters? Which kind of lightning conditions we expect? Which kind of acquisition equipment we expect? So if we want to target people in the plant taking pictures, maybe all of them will use the work phone, which is the same for everyone. Maybe if it's for the end user, people like me, we will need to account for different phones, different cameras. And then the answer to these questions that the domain knowledge must bring will define how much data we need. So here the data scientist comes. It says, okay, we need to have a representative test set, but the size of this test set will depend on how diverse we expect the data to be. Then we move to image annotation. And here we need to know, okay, are we relying on internal or external labelers? Do we need subject of matter experts to label this data? If not, let's design some nice instructions following some guidelines. And only then we start to annotate this data. And finally, we make sure with like a big checklist of what to check when. We also have tools available, like I said, Voxel 51, or even custom dashboards to check for the quality of these annotations. Sometimes we might need two annotators looking at the same image to see if they agree, to see if labels are reliable. And then for the cleaning, we should check what to do with low quality data. Let's discard them or let's improve them. Wrong annotations, how to spot them. Ambiguous annotations, how to deal with them. So we guide this team through all these steps. We spend a lot of time on data related topics, and we believe that once this is nicely done, we will save a lot of time when training and evaluating the model. So the main takeaways here, I would say, is to really design these standards and processes, for instance, for data collection, but also for others, because it really accelerates all the projects that might come in the future. And we are definitely focusing a lot our attention in data-centric approaches. So thanks a lot for your attention. I wish I could have more time to bring some more examples, but please feel free to get in touch. I would like to hear more about also your experience, your challenges, how you are tackling them in your companies. Yeah, and now I will be open to questions. Thank you.